Um, so part of the seminar, and I'm very happy to give it to this audience, started 4 years ago for Uzis Milansky's zillionth birthday, where I was adopted by Eisenman family. And I was watching over Michael's shoulder his work on Ising model and zeta functions, which I didn't realize how zeta functions are relevant. And the light went on, so part of what I'll talk about is only possible by being physically together and learning from each other. But often in last 4 or 5 years, people ask me, it's a field theory. What do you mean it's a chaotic field theory or turbulent? What do you mean by this? Part of the reason is that in quantum field theory, this has been an active topic in about 4 or 5 years. And I have a simple answer. It's very clear, and everything I'll tell you today is classical, even though it's connected to many, many things, let's say hard binding models, Harper's models, anything you want. But the idea is very simple. So I will do it in 3 stages. I'll first tell you what chaos is, the way we teach it in a very elementary undergraduate course. Then we'll move to the graduate school, and I'll tell you what chaos is when you do field theory. I won't tell you about what we really want to do is we want to describe turbulence in Navier-Stokes, but also in quantum field theories in this way. That is another seminar. So here is very brief a motivation. In recent years, I've worked on turbulence, and great advances have been made in this millennium in the subject, from my theoretical prejudice point of view. So here is a typical simulation of turbulence close to the onset of turbulence, not for very high Reynolds numbers. And what's striking about this is that it has a recognizable structures. Now, simulations and experiments are done on what's essentially infinite length pipes. So they're translationally invariant along the pipe. What the theory does is it's able to cover short periodic sections of a pipe. One question one could ask is, can I use these blocks, which I understand in detail, to build up turbulence? What would that theory look like? So that's, one of the possible motivations. There are many motivations, what I say. So we would like to build up a chaotic or turbulent field theory from simplest blocks, putting them together. And we'll do it in the usual ways, the way we write laws of nature. We'll demand time invariance. The law will be the same today and tomorrow. We'll law space invariance. Measurement in Kyoto is same as measurement in Atlanta. If you fall asleep in a minute from now, please take this as a take-home lesson. You are all familiar with what I would call harmonic field theories. So these are theories where you have matter, you bang it, and you get oscillatory modes. In condensed matter, this is called tight binding model. In applied math, it's called Helmholtz. And you know that you're supposed to write normal modes of this thing, and you understand it. Now, chaotic field theory is the wild sister of this harmonic field theory. Instead of having springs at every side, you have rotors. And instead of having this tight binding model with oscillatory modes, the solutions are actually solutions of Euclidean Klein-Gordon field theory, or what applied mathematicians call Dam-Poisson equations. So this is all I want to teach you today. If you now space out, please remember that. What is chaotic field theory? It's a field theory which is every place locally unstable in very precise manner. And if you know something about dynamical systems, the usual field theories, the way we teach them, the kind of thing before we add couplings and perturbations to them are oscillatory eigenmodes. So, the elliptic behaviors around the resting point of the system. For chaotic field theory, everything turns hyperbolic. Everything that you push, it doesn't push back, but just runs away. And that's herding cats. I'll do it the way that Mephistopheles says. You have to do it 3 times. So I'll do it first for the coin toss. I'll explain coin toss the way ergodic theory thinks about it on a undergraduate level. And then I'll do it how the field theories should think about it. Most of them don't, but they have all the tools to do it. And then I'll repeat the same thing for mechanical system. And then I'll explain, what space-time chaoticity is. Time evolution formulation is the way we usually think about chaos, deterministic chaos. So the way we explain it, we say, suppose you're throwing a coin toss, and it's not a loaded coin, so it falls face and tails the same way. One way to write a model is so-called Bernoulli map, in which you say, my initial coin has conditions any place on the unit interval. I throw it, and depending whether I fall on the left or right half of the unit interval, I say it's face or tail, and then I repeat this. And repeating it means that I again throw it over the whole interval. That's done by the slope of map of slope 2 called Bernoulli map. And if I keep doing this, I'll get this. It's deterministic process because it depends on initial point, which is some typically normal real number, usually, not rational or anything. And that's the essence of deterministic chaos. We usually write this as modulo 1. So if I'm on the right-hand side of interval, I get stretched by 2, but I get put back into the unit interval, and that's what this modulo 1 does. Now let me just look at what this modulo 1 is in more detail. So the map is, all initial condition gets stretched by a factor which is 2 or larger. I'll use only integer stretching factors in this talk. So that's, the essential instability of chaotic systems. Every time I repeat this, neighbors get separated by a factor of 2 or factor of s. And then I construct the process that repeats itself saying, I don't want to run away. I have to be confined. So what I do is I subtract the integer part of the result here and subtract it. So I'm confined to the unit interval. And now I have a field, what I'll call a field at time t. You'll see why. And I can specify my whole trajectory through this space of repeated coin tosses by saying it's face or tails, or if it's loaded dice, it has 6 possible values. So I have an alphabet, and that's the integer part of this. So for example, if I'm trying to model a dice and I say it's a fair dice, when I throw it, I have 6 faces. So I can find an analog, which is a Bernoulli map of slope 6. And then I have to, say at the initial point, I'm in one of the 6 intervals and I remember where I was. After a toss, I can land any place. It's done by this slope of slope 1. Not to run away, I have to take modulo 1, and I do this by subtracting the integer, but I keep repeating it. So that's chaos. What happens is to specify future, I have to be more and more precise about initial conditions because I have to be in smaller intervals to get the desired sequence of coins on tosses. And if I do this n times, I'll get 6 to the n possible ways of having sequences of coin tosses. And now I'm ready to define what is chaos, undergraduate. Chaos is positive Lyapunov, which is this stretching rate S, slope of this thing. And its logarithm says, how much I stretch per throw. So it's a stretching rate. It's called Lyapunov. And then I have to count possible ways I come back into the same interval. So possible walks through this symbol dynamic space, possible sequences. I take the logarithm divided by n, and that's a rate of how often I come back or how many walks I have. And that's called entropy in dynamical systems. And chaos is positive Lyapunov and positive entropy. That's chaos, deterministic chaos. Lyapunov measures how quickly I escape any neighborhood. It's a local escape rate. Entropy measures the number of ways I can come back because I'm confined. I'm not allowed to exit the world of tails and faces. So this is traditional way of defining chaos. And it's a deterministic procedure, but if I coarse grain it, it looks probabilistic. So that's a connection to statistics. Now, in third millennium, actually in whole last century, we've had special relative field theory. We know that space and time are really pretty similar. So let me do the same thing in a way you haven't seen it on a lattice. It's totally trivial. Everything I'll explain for a while, you can do by, on piece of paper, everything is fine. So time evolution Bernoulli map says, I have some initial state phi, and then the law of motion tells me what the next state is. And if it's outside of unit interval, I have to subtract the integer part of the result. And let me just move this on the left-hand side. Now, this is called one-step difference equation. And now I think of a temporal lattice. So I have a one-dimensional lattice of points labeled by integer z, plus to minus infinity. And on each side, I have a field, which is, it'll be height of my cat or something. And I have a label saying, it's sitting in one of the intervals. So it'll turn out to be a source in the way I'll formulate it. And now, if I have an n lattice segment from this infinite lattice, I can write this as a vector of fields, n fields, and vector of symbols. And as you'll see, these m's are really the marching orders. If you specify sequence of m, it orders me how to do this, and there will be unique solution to this problem. So this figure might not be very useful to you, but the way I think about it, there is a temporal lattice, just a lattice, and at each lattice site, there is discrete instruction saying there's a bunch of values here and I have to be one of these values. And then there is a law, which in this case is a Bernoulli law, that tells me what the field is on that site. And then I'm supposed to walk through Bernoullistan. This is this landscape. So when you do this as a field theorist, you think globally. You think of the whole configuration, this vector of n states. And what it has to do, it has to satisfy Bernoulli condition at every lattice site. So the difference of the difference equation has to have a value of the source. You'll see why I insist on fields and sources pretty soon. And you can write this as a matrix equation that acts on the whole state at one go, following the marching orders. And this little sigma is a shift matrix. It just says I'm supposed to compare values at different sites. And this is the law. And I have to do it. Law says compare the neighbors, and they have to add up to this integer value. How do you solve this? Well, let me write the law as curly J. I will call it Hill matrix, following tradition that you call everything by after dead white men who haven't done it. But I think Hill and Poincaré deserve the credit here. You put everybody on one side and you're looking at the zeros of this function. In this case, it's a linear thing, so it's not so hard to solve, but this transfers itself to Kuramoto, Shivashinsky, and Navier-Stokes, etc., where this is a nonlinear condition. And now the entire global lattice state is a fixed point in a unit cube, in an n-dimensional unit cube. So we have converted the problem of finding allowed walks through Bernoulli into a fixed point problem. It's a fixed point condition. And one way you can solve fixed point condition in general is you can make guesses what a solution is and then use Newton method to improve your guesses, which means you need a first derivative of a fixed point condition. And this I'll call orbit-Jacobian matrix. It is what happens if I have a noisy solution or I perturb everybody on the whole lattice and I measure the effect of that. Now, what does this global Jacobian matrix do? It does two things. The first one is, educational surprise for me. I had no idea that's what it does. And second one is what Hill did when you study orbits of the moon, between Earth, perturbed by Earth and Sun. So let me explain what fundamental fact is. It's really cute geometrical understanding of what this is. To satisfy this condition, I take a set of fields. So this is the lattice fields. I multiply them by my law J, which turns out to be an integer matrix in this particular application. The result has to be an integer because m's an integer. This has to add up to the 0. So what the Jacobian matrix, orbit Jacobian matrix does is takes the unit hypercube, phi sits in the unit hypercube, stretches it out and into something called fundamental parallelepiped in any dimension. And then every periodic point, every solution has to be mapped on the integer lattice, and then you translate it back to solve this equation. So it turns out the number of solutions is number of integer lattice point within a fundamental parallelepiped. And now comes the fundamental fact. If you take the determinant of this orbit Jacobian matrix, I'll call it Hill determinant unless somebody teaches me something else. The Hill determinant counts the number of the solutions. So one interpretation of this perturbation of the solution is that its determinant counts all possible solutions. To give you a little example, if I look at the periodic things of like 2, so I have just two-dimensional vector, then unit cube is unit square. Now Jacobian, in this case, stretching by a factor of 2, like in Bernoulli map, just takes the square, maps it into a parallelepiped. And what it does is that there is a fixed point at the origin, 0 remains 0, but then there is a 2-cycle in a big space, and it maps it on integer points of that lattice, and notice the volume of this thing is 3, and this is number of solutions. So that's what fundamental fact is. It's a very nice geometrical picture. In 3 dimensions for cycle 3s, you can still draw it and you can turn it around. I won't give you a simulation, but it sends a cube into fundamental parallelepiped, which is same dimension. And if you count all the integer points in it, indeed you find all the solutions of period 3, so lattices that satisfy the Bernoulli condition. And this is always true. Here is the other interpretation, which is more familiar to us. We are looking at the whole state on a lattice, and we are perturbing everybody. I'll call this orbit stability. So this is stability under global perturbations of the solution, whereas dynamicists are used to the idea of evolution in time. They still think like nothing happened since Newton, no special relativity, no nothing. What they do is they start with some initial condition like Lorenz has. Lorenz model has 3 dimensions, so it's 3 by 3 matrix, and you propagate this in time. Hill in 1886, an American astronomer who left Yale because he didn't want to teach stupid undergraduates and did this at home, perturbations of the moon. He wrote this amazing formula which says the determinant of perturbation of an orbit every place along the orbit is the same as determinant of 1 minus jm, where j is a little thing moving forward in time. So this is temporal. This is how we usually think in the dynamical system. This is entire orbit. That's how we think in field theories. And it took Poincaré to prove this is correct because the left-hand side is a huge matrix. Because if you have a continuous orbit, then this is a functional matrix. But the right-hand side is a tiny little matrix. And it's a beautiful relation between thinking forward in time and thinking globally, locally versus globally. So now I can tell you how field theorists should be thinking about chaos, and I'll now repeat it twice in this talk. So chaos is expanding Hill determinants, meaning when you look at determinant of J, it has some eigenvalues, this matrix, which are larger than 1, so neighborhoods are expanding. And exponential number of different configurations for any compact sublattice of the system. And this is precise sense in which deterministic field theory is deterministically chaotic. And I beg you to notice one thing, and it's very hard to unprogram yourself. There is no notion in time in this definition. We have configurations. These are the solutions on a lattice. They have their stability, which is perturbation every place. No time, it's just a lattice. And we count them, we count the configuration. And that's why, visiting Michael Eisenman was so useful. I realized, well, this is like Ising model, but and that's the way to think about it. There is something that's a graduate level in dynamical system. It's called periodic orbit theory. You can be more sophisticated about what we're doing here. And, you can notice that when you think of a periodic orbit in time, first reference I found was Azaria del Almeida in 1984. I myself did it a couple of years later, and everybody else did it at some point or other. They stated very clearly the number of periodic points is related to the time evolution Jacobian matrix by their ergodic intuition. They thought, we have a phase space, it's compact. And ergodicity means there are points every place on it. And in some sense, they have to be uniformly dense. In particular, if I look at periodic solutions, they sit someplace in this phase space. They have a property that in finite time you find them and they're there forever. And they're all repelling, they're unstable. So they push other periodic points away of them, and there's some kind of balance. They called it principal uniformity. And it said if you take periodic points, weigh them by their natural weight, which turns out to be determinant of the fixed point condition inverse. So if this guy's unstable, there's a number smaller than 1. And that's how you could use periodic orbits to describe what happens in an ergodic system. Now they're nice in the sense that rational numbers are nice. And you're trying to describe what happens for any number unit interval. You can use periodic orbits to describe intervals or neighborhoods. So that's why Hill determinant, which seems to have nothing to do with counting, that's why it counts. Now, in more modern periodic orbit theory, which you can find for free on internet by looking at chaosbook.org, there's something called conservation sum rule, which is the same thing. It says that if you take orbits of certain length, so all configurations of length n, their weights should add up to 1. It's basically probability conservation for the dynamical system. So it says periodic orbits divide neighborhoods in a precise way. And Hill and Poincaré say that this forward in time weight can be given by global stability. For Bernoulli system, we can go back to undergraduate course. The stretching rate is same every place because it's a linear map. So all of these determinants are the same. And the number, we already did this by fundamental fact, number of orbits is determinant J, but now if I look fundamental fact in reverse, fundamental fact partitions original square into neighborhoods. And each neighborhood has a weight. And that weight in this particular case happens to be 1/3 of the unit square because this is a simple example. And we can partition by the weight. You can ask, okay, you can do this for n equals 2, n equals 3, n equals 4. Who cares? If you can you tell me how to do it for arbitrary n? And the deep idea there is zeta functions. It says I should write a generating function of all possible numbers of solutions. And that generating function ultimately goes back to Euler and then Riemann and has many, many reappearances in mathematics. Basically, what the generating function says is if I take a logarithm of determinant, I can write it as trace of logarithm for any matrix. But this rewrites volume in terms of traces, meaning loops. That brings in what's called a zeta function. So determinant of my operator that's generating stuff can be written as sum of traces. These traces, you can understand them as number of periodic solutions. And that's called a topological zeta function. It just counts numbers of solutions. It has 1/n because they're all cyclically invariant. If you have one solution, you can translate it around the ring n times. That's why 1/n is this. And brilliant thing about this is zeta function only cares about orbits rather than individual solutions because they come in families. It's even more brilliant than that. It doesn't care about orbits, but it cares about prime orbits, which are the shortest non-repeating orbits. So this is generalization of notion of prime number versus natural number. That's how Riemann and Euler come into this. In this particular case, we have explicit solution for number of prime orbits. We put it in here and we get a rational polynomial. So zeta function is brilliant. It's extremely simple, especially a topological Zillian function. It says this is what generates all solutions and the problem is solved. And this is periodic orbit theory. And now you got starting graduate course in chaos. It's not just deterministic chaos, but you can totally solve it for systems which are nicely hyperbolic and have what's called a finite grammar, where you can describe the possible symbolic sequences. And they're described by rational polynomials. And here credit really goes to Smale and Smale School. So to summarize, what's deterministic chaos in a modern way? You have to find solutions of your law, of your equations of motions, and you find them globally as fixed point conditions. Then you have to understand their stability. That's described by orbit Jacobian. If orbit Jacobian has expanding eigenvalues, That's called chaos. Everybody is unstable because eigenvalues are expanding. Fundamental fact tells you what the number of solution is. Zeta function tells you how to generate all of the solutions. Okay, that's it. The first time you had a course in chaos, now you're actually in the beginning of the graduate school, but in the third millennium. But then, this is good enough in math, except I'm supposed to call it theorems and lemmas. But it's not good enough for physicists because we don't have time for this nonsense. Because what do I care about Bernoulli map? I've never seen it in my laboratory, right? If I'm a quantum kind of person, I know that field theory should be Hamiltonian, energy conserving. I can't do quantum mechanics without it. That's what physics is. So I'll do it second time, and I'll do it not by this silly Bernoulli map, which is some kind of child's game. I'll do it for a real problem done in Novosibirsk, for example, a mechanical problem. And the way we do this, we don't look at this Bernoulli map, which is really partition of a circle because it has this periodic invariance. We look at mechanical rotors. And, there are two versions of it. So I'll define field theory for a mechanical system, so something I can quantize. First, the way we always do it, which is Hamiltonian. And then we'll do it in a second way, which, people don't feel as comfortable with unless they're engineers and field theorists. And that's much more smart. But anyway, let's do it the usual way. So the usual way we teach chaos for people who care about physics, we say, look, think of an electron circling an atom, and I shine laser light on it. I want to ionize it. So that's called a kicked rotor. And I look at the simplest solution that it runs on a circle, and at every time t, instead of having a sign exciting, I'll give it a kick. That turns it into Taylor-Cherenkov and Green standard map, where the time intervals are these labels here. And this is Hamiltonian system because it says velocity, discrete velocity. This is defined by delta t, which I've set to 1, equals momentum. And change derivative of momentum, that should be acceleration, right? Or force. This is given by the kicks at time t. And out of this come all these beautiful pictures you have seen about chaos and Hamiltonian system. Standard map is always the most beautiful illustration, where you see islands of periodicity, chem, tori, stochastic web, hyperbolic things. But let's consider the simplest possible case of it, where the law F is a linear law. In that case, this becomes a linear mapping from P and K to P and K later, one step later. And it has a property that momentum can diffuse. But then we do the same thing as we did with Bernoulli. We say, look, let's keep momentum in a unit interval. So we add a modulo 1. For the angle x, there was always modulo 1. I was on the circle, but now we make also momentum. So we put the whole thing on the torus. And if k is an integer, you can show that this is continuous automorphism of the torus, or a Hamiltonian cat map. It's linear, in this case, area preserving. There is a surface of the torus, map of torus into itself. And the only thing that in that case matters, this law has to preserve volume, so it has to have determinant 1. And the only invariant left is a trace of determinant. And this trace is called a stretching factor. So if trace is larger than 2, it turns out that this is hyperbolic system. Easy to check. It's beloved by ergodicists. It's the perfect chaotic Hamiltonian dynamical systems. And you might not like to live on a torus, it's called an osso, etc. But you cannot have a better illustration what chaos means in determinism and Hamiltonian setting. And if S is smaller than 2, then the solutions of this problem turn out to be sines and cosines. And what it means is that if I have some resting point for the system, if I perturb it, it oscillates around. So it follows the Hooke law. But if S is larger than 2, then we have the anti-harmonic sister of the Hooke. It's totally wild because what happens is instead of sines and cosines, you have hyperbolic sines and cosines and solutions. So everybody runs away. It's like cats just scattering out. But as they live in torus, they have to come back. So cat is important for physicists because it's to chaos what harmonic oscillator is to order. There is no more fundamental way of explaining what chaos is in mechanical systems. And that's why we care about it, even though we don't live on a torus. It seems unphysical, but it's very good to teach you what chaos means. Third millennium, and it started in, for example, by McKay and Mies in late 80s. Whenever you have a Hamiltonian system, you should describe it also in Lagrangian way. That might be a good way to do it. So Lagrangian formulation says, instead of momenta, use velocities. In this case, velocity on discrete lattice is just 2 nearby points divided by their distance, but we said delta t equal to 1. You rewrite your equation forward in time, you look at it, and you realize that when you multiply this matrix, we have a very pretty two-step difference equation. It says, if I'm on lattice side T on one-dimensional temporal lattice, then I have to see what happened before and what's going to happen next. Now, my law on the lattice is that I get stretched by this factor S, which is this trace of my matrix. And I have to make sure that I am in the unit integral. So if I stick myself out, if S throws me out because it's larger than, it has to be larger than 2, 3, 4, 5, 6, I have to subtract integer part. So this looks like Bernoulli map, but it's very pretty and it has a symmetry because the system is time reversal invariant. So, what's future, what's past doesn't really exist on this lattice, it just has reflection invariance. So that's what cat map is. You again have to think globally as a field theorist, but you have to make sure that locally the law is respected. So local law is, for every 3 points on this lattice, I have to satisfy my marching order. And but global equation is the same, it's just this matrix J is a little different. And I'll have to find its fixed points. J matrix now, is a Toeplitz matrix, tridiagonal, etc. And solving this problem is just what I did for Bernoulli, but now it's physics. And it says, I have to find zeros of this for any finite segment. And zeros all sit in unit hypercube again. The fundamental fact works again. So if you take unit square and multiply it by a cat kind of Jacobian, it stretches it into a bigger square, which has volume 5. And indeed, you can count there are 5 periodic points. So the fundamental fact work. And more amazingly, you can add them up to all orders, discounts of Hill determinants, stick them in topological zeta function, and you get this beautiful explicit formula due to Isola in 1990 that says the zeta function is the rational polynomial, where in numerator I have the stretching factor, in denominator I have something that turns out to be Laplacian for one-dimensional lattice. And this problem is totally solved, just like we did it for Hill, but now it's physics. Now, to experts of ergodic systems, they always teach it as, you take in time, you take a partition, you slice the cat into the pieces, you recombine them. Here is one explicit example how to do this. That's called otherwise generating partition, or Arnold cat. And it's a distraction. What I just taught you is much deeper insight. I don't need to do any generating partition, just for specialists. To understand that, think about what is temporal cat discretizing if I take a limit of small time steps. Well, it's a three-step difference equation. Compare it to Laplacian in one dimension, which says, I looked at my neighbor to the right, neighbor to the left. I take twice of my height, I subtract. And if that's zero, I'm on a line. But if it's not zero, I'm measuring curvature, and that's done by Laplacian. That's a discrete Laplacian. And then subtract these two things, and you discover that what cat map is, it's Klein-Gordon equation, or Damp-Poisson equation for applied mathematician, that says, Laplacian plus the mass square of a scalar particle has to satisfy marching order. So this is how a field theorist has to think about a cat map. It's really just one-dimensional Klein-Gordon equation. To remind you, Helmholtz equation looks like that. If k is imaginary, in imaginary time, this has oscillatory solution. If this goes imaginary, then it's called Klein-Gordon, Yukawa, screen, whatever. They're very close relatives. One of them has sinusoidal solution, other one has growing and decaying exponentials. So the cat mechanical system is just a Klein-Gordon equation. And we have already solved it completely analytically, done. We have zeta function. To repeat myself, to solve this problem, thinking globally, you have to find all fixed points of the law on the whole lattice. You have to study their stability, and then their stability, their fundamental fact enables you to count all your solutions, so you're sure you haven't missed any. And if you're really smart, you can summarize all this as a zeta function, which describes everything that the deterministic chaos can do, also for a mechanical system.
Viewing these things as lattices, I mean, as a condensed matter physicist, you always start thinking about what about boundary conditions? Can you impose some boundary conditions in time direction?
I glossed here. Thank you for asking me. In this context, please don't use anything other than periodic boundary condition, because everything is defined by translational invariance. So the only boundary condition that makes sense is translational invariant. Gutkin and a number of other cats have written paper with reviews the Dirichlet boundary condition. It's painful because you have broken the invariance. It's not worth your time. Always periodic. I'll move on. Now we can do this third time, but now we do it in any number of dimensions. So what we do is we take a lattice in d dimensions, and we put a cat at each side of the lattice. And we say, this cat can talk to its neighbors, and it has to stretch according to the law. In this case, you can do it Hamiltonian, but it's a waste of everybody's time. It's ugly. We have to do it because we always have to convince people that special relativity is consistent with sitting in some stupid frame and evolving in my time. But Lagrangian is the only way to go. So there is a lattice. Each cat has a name. These are possible states of cats. And on every cat, every side there is a cat. And now they will do their thing. So how do you do it? to train, take us one dimension in space, and we inherit the time because cats sit on the temporal lattice. So now we are in two-dimensional spatiotemporal lattice. Require that each cat talks to its neighbor to the left and right in space, n+1 at time t. Require that the rule in which cat interact is same in Kyoto and in Atlanta. Translation, spatial. We don't care what's left and right. That's a prejudice, sinister or not sinister. So if I flip it, it should be the same. So I require spatial reflection. Now I already have this time thing, and I already had time reflection built in and time translation because the law should be same today and tomorrow. And I just add one more thing to make this simplest possible problem. I say, look, the strength with which I interact with my left-right neighbors should be the same as the strength with which I interact myself in the past and future. In other words, I add a space-time exchange. And Gutkin and Osipov did this in 2016, and they got out of this a two-dimensional couple map lattice, which looks very much like the one-dimensional, except now you have to compare neighbors in space and neighbors in time. And then you have to stretch yourself, and it turns out dimension of the space comes in here. And that you have to make sure that this answer is in the unit interval, so you have to subtract, as always, our non-integer part of the answer. So that's it. So it's constructed from invariances, translation in space, time, reflections, and interchange space of time. And this is not, I have to emphasize, it's not Bunimović. I know Lorna is there. It's not Bunimović and Sinai, and Katok and Sinai who did it for cat maps, because it's kind of in a different opposite end. I mean, for them, it was very important the spatial coupling was weak, so deformation of cat map, nonlinear deformations was small, so one could use the same Markov partitions, but we don't partition anything. There are no Markov here. That was for the expert. So now let's write this in continuum. Laplacian in two dimension compares four neighbors with where I am. Subtract this from this law of cats that governs cats. And now the herd of cats is governed by the d-dimensional law, where Laplacian is balanced by parameter mu square, which cares about whether S is larger or smaller than 2. If S is larger than 2, this is a positive number. If S is smaller than 2, then it's, it means that mass is imaginary. And the law that d-dimensional spacetime cat is, if you wish, momentum squares plus mu square equals phi z. You recognize it. This is, you've always seen field theory for scalar fields. Now, if mu square is negative, this is called tight binding model for condensed matter people, or Helmholtz for applied math people. And we know the solution, there are sines and cosines. If this is positive number, this is called Klein-Gordon, Yukawa, Poisson. And the nonlinearity, this is, linear problem. Nonlinearity is hidden in the sources. That's chaos for field theorists. Traditionally, in field theory, we think of the ground state as being lots of oscillatory mode. These are, vacuum fluctuations over there. And then we stick in couplings. So we let light and electrons couple free. They just oscillate, but now they couple and do perturbative calculations. Now, if they're strongly coupled, it's a hard problem, but main thing is everybody is oscillating. In chaotic field theory, everybody is a crazy cat just running away. Everybody is unstable. And the trick in this exposition which follows the classical way we explain what chaos is, that they all run away, but they're all confined on their torus. They can't get taller than one. So they have to come back. Now we have told the story 3 times. We can solve it, and it's always the same story. We're giving marching orders, and now the marching orders are on every lattice side. So the table, symbolic dynamics, is now a block, a brick of things. You specify the table. I go to my computer. I solve either this problem or a nonlinear problem like Navier-Stokes. And I tell you, there is a physical state which has this description in terms of symbols. I'll do this just in 2 dimensions. Same as always. I have a state, I bang it by the matrix. It turns out, the way I think of it, I have a state, I have to satisfy the tangent condition that's called differential equation or law of motion every place. And I solve that problem. And there is a little thing that happens here, which I find very confusing. Now I have to solve it on tiles of different size. And it's very tricky to count these tiles. It's kind of condensed matter, but they're all relative periodic. Here are samples of what tiles look like. There is confusion about, there are 2 integer lattices. The floor on which the cats are is a lattice, but also my states are in a different Z1 lattice. Fundamental fact still works. I can write it in kind of block matrix form. I can write these Jacobians as matrices. I can compute their determinants, and I can compute them for arbitrary stretching factor. And typical answer is a multinomial. In the stretching, we can tabulate as many as you want. So we can systematically find longer, larger spatiotemporal periodic solutions. We can count them. Tricky thing is we can find the ones which are called prime orbits, which are the shortest ones, which are not tiled by the shorter ones. We can do all this, but we can't write elegant zeta function, and that's why I'm giving this talk. Somebody in this audience might know it. I think zeta function looks something like that, but I don't know. And I'm not alone. In Zetastan, everybody has visited Zetastan sooner or later who does condensed matter, number theory, cryptology, engineering, discretizes any problem. So there are infinitely many papers. I just give you a few of people who have to compute Hill's determinants, including Michael Eisenman. And it's hard because it turns out there is unimodular invariance. Defining lattice is hard. So this is the same problem as understanding, what the fundamental domain is in modular formulations of these problems. And I need your help, but okay, because I can't put together this zeta function for spatiotemporal case. It's some kind of elliptic function, and somebody will tell me how to do it. In the following sense, I haven't emphasized yet, because there is shadowing. If I have regions which have same names in symbolic dynamics, I can show that the distance of the states in these regions, so difference, pointwise difference, is exponentially small in the middle. So even though I don't have loops anymore, I have tori, they shadow each other. That's it. Now I just want to say a few things, what it all means. What have we learned? When you think of field theory, please don't involve initial states. It's impossible. You have to think like in statistical mechanics, you have to enumerate configurations. So the theory has to be formulated in terms of periodic tori rather than time periodic loops. Dynamics has gone away because there is no time. Your goal is to find all possible states, enumerate them, and then compute them. There is no more time. In the seminar, I've committed the crime of the century, which Central Europeans will understand, and Descartes will understand. The time is dead. Don't think in time. Time is gone. And how you solve these problems is in Bernoulli land, you solve everything globally, like Hill and Poincaré did. And the stage is set for quantum theory, which I'll let other people do. I'm done. And all theory is grace, as Goethe. Thank you for the opportunity to talk to this group of friends. Thank you very much.